Magnetic resonance imaging, or MRI machines, are powerful diagnostic tools that use strong superconducting magnets and radio waves to generate images of the body's soft tissues. Here we'll see exactly how the magnet's field interacts with the body to make those images. The human body is made up mostly of water molecules, or H2O. So it contains lots of hydrogen atoms. These atoms react in a very useful way to an MRI's main magnetic field and the radio waves it emits. In the nucleus of every hydrogen atom is a positively charged proton that spins around an axis, like the planet Earth, spinning with a north and a south pole. Normally, these hydrogen protons spin about willy-nilly on randomly oriented axes. Put them inside an MRI machine, however, and things change. Suddenly, the axes of the hydrogen protons realign with the powerful magnetic field and spin, just like a top, at a specific frequency, its resonance frequency, that is a function of the strength of the magnetic field, represented here by blue lines. Half the protons face in the direction of the field, and the other half in the opposite direction. Well, not exactly half. There are a few more hydrogen protons arranged in opposition to the magnetic field than there are arranged in alignment with the field. Those protons, lacking a match among the oppositely aligned protons, are the protons targeted by the MRI scanner. Inside the MRI, an RF coil is placed near the part of the body being scanned. This is a radio antenna that transmits and receives radio frequency, or RF waves. The MRI technologist uses it to send RF pulses at the resonant frequency of the spinning protons. When the RF coil is turned on, the unmatched protons absorb the energy of the RF waves, which causes them to flip on their axes. They're still in line with the magnetic field, but now in the opposite direction. When the RF pulse stops, the protons release that absorbed energy, return to their previous alignments, and, in so doing, emit a signal back to the coil. Let's watch this one more time. The protons absorb the energy from the RF waves, then flip on their axes and emit the energy back to the coil. That signal gets turned into an electric current, which the scanner digitizes. The scanner processes the signal using advanced algorithms in order to produce the image. Tissue with less water in it will have fewer hydrogen protons to emit signals back to the RF coils. Those areas appear darker on MRI scans. The varying signal strengths get translated into various shades of gray, which radiologists recognize as different types of tissue on the scan. MRIs can be used to scan the brain, joints, and other parts of the body in order to highlight abnormalities such as herniated vertebral discs, cancer, stroke, broken ligaments, and aneurysms. The radiologist uses multiple RF pulses at different powers and in different sequences to manipulate the signal from those parts of the body.